तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last few lectures, we considered permutations and combinations. We also considered generating functions and also distribution of distinct and non-distinct objects into distinct and non-distinct cells, which also included partition of integers. So, these are some of the topics which are covered in the last few lectures, and today we shall consider recurrence relations and how to solve those recurrence relations, what is the use, and also how to use generating functions for solving such recurrence relations. Now, what are recurrence relations? Suppose you want to ask a person his age or her age, whatever it is, then you do not feel like asking directly, or he may not be able to, he may not be willing to tell directly his age, but he may say that he is 5 years younger to his brother and his brother is say 45 years old. That means he is 40 years old. You can calculate his age from his brother's age. So, instead of directly telling, you can indirectly say that. Or suppose you want to ask a person a route to go to the post office, you ask a person how to go to the post office. He may say go from here few yards, then turn left, then 10 yards, then turn left, then 100 yards turn right, then 200 yards turn left. Like that he can give instruction, which will be difficult for you to really memorize and then go on keeping the route to reach the post office. Whereas he may give the route like this: from the shop, a particular shop, you have to go right and turn left, then you will reach the post office. Then how do you go to that particular branded shop? From a particular school, you move north and then east, you will go to that particular shop. Then how do you reach that school? From here you go 100 yards towards the east and then turn left or something like that. So, step by step he can give the direction how to reach the post office, instead of telling go right, left, right, etc. He can say that from the branded shop you have to go like this to reach the post office, and to reach that particular shop you have to go from the school in this direction, and to reach the school you have to go from here like this. So, something like that he can explain. That is the underlying basic consideration for the structure of a recurrence relation. They are very useful. We shall consider one or two examples. For example, let us consider first a very simple example of a recurrence relation. You know what is known by the Tower of Hana problem. Tower of Hana. That is, you have 3 pegs, A, B and C. 3 pegs you have, and on one of the pegs you have n circles, n blocks. The lower one is bigger than the next one. They are arranged in the increasing order of their decreasing, they are arranged in the decreasing order of their width. Circular objects are placed on this peg. Now, you want to transfer all these circular disks to B in the same order. Ultimately, you should have them in these circular disks in the same order. And for transferring these, I have drawn 4. In general, there can be n disks. You have to transfer them from A to B, and at the end you should have them in the same order here. But while doing that, you can use peg C in the intermediate steps, but you have to do it in such a way that at no time a smaller disk is below the bigger disk. That is, I cannot say if I number them as 1, 2, 3, 4, I cannot transfer 1 to C, then 2 to C, then that means 1 will be below 2, 2 is bigger than 1, that cannot happen. So, at all the time the smaller one should be above the bigger one. Can you transfer like that from A to B? And if so, in how many number of steps? If you have n disks, in how many number of transfers you would require to do that? For example, if I have only one, it will take just one step. If you have only one, obviously you can transfer like this. If you have two, the first one you can transfer to C, then the second one to B, then the first one from C to B. In 3 steps you can do this. Transfer from A to B the 2 disks. In general, if you have n disks, what is the number? Suppose I denote the number as an. What I have to do is, I have n disks like this, smaller, n disks. So, first I transfer n minus 1 of them to C in this same order, smaller one upper and the bigger one lower, using B as the intermediate peg. In that case, how many steps it will take? If I denote this by an, transferring n this I denote by an, transferring n minus this, it is an minus 1. So, what do you do? From A you transfer n minus 1 disks in that order to C using B as a intermediate peg, which will take an minus 1 steps. Then the last disk you can transfer from A to B, which is 1 step. And then after transferring the last strip here, last disk here, this n minus 1 disk again you can transfer from C to B using A as the intermediary peg. Again that can be done in an minus 1 steps, because we denote by an the number of steps required or number of transfer required to transfer from one peg to another in the same order, such that at no time a bigger disk less on a smaller disk. So, you can see that the number of steps required to transfer n disk will be twice the number of steps required to transfer n minus 1 disk plus 1. So, this is called a recurrence relation. This type of an equation is called a recurrence relation, and the number of steps is really given by 2 power minus 1, which you can see. So, once you obtain this relation, how do you solve this? There are 2 methods. One is an ordinary method, the other is by the use of generating functions. So, as an example, let us look at this. Consider the numeric function a is equal to 3 power 0, 3 power 1, 3 power 2, 3 power r. Clearly, this sequence, this is a function AR is given by 3 power r. The function can be specified by a general expression for AR, namely AR is equal to 3 power r, r greater than or equal to 0. Now, we will see later how to solve such equations by generating functions. This function can also be specified by its generating function, namely Az is equal to 1 by 1 minus 3Az. If you expand this, it will be 1 plus 3z plus 3 squared z squared, etc. So, the coefficient of z power r, general term will be 3 power r z power r. So, the coefficient of z power r will be 3 power r, and that is what is given by this. Okay. This. So, the generating function for this is 1 by 1 minus 3 z. And the relation, recurrence relation is AR is 3 times AR minus 1. It is a geometric progression really, but you can very easily see that AR is equal to 3 into AR minus 1. So, either way you can specify it as AR is equal to 3R, 3 power R, or A is the generating function is this, or AR is equal to 3 AR minus 1. With that information that A naught is equal to 1. So, to start with, the first point is A naught is equal to 1. This is known as the boundary condition. Also comply, this completely specifies the numeric function A. You also know this example, which is very common. The Fibonacci sequence of numbers is given by 1, 1, 2, 3, 5, 8, 13, 21, etc. See, first two are 1 and 1, the third one is obtained by adding the first two, the fourth one is obtained by adding these two, 1 plus 2, 3, then 2 plus 3, 5, 3 plus 5, 8, 5 plus 8, 13, and so on. This is the way you get the Fibonacci sequence, and it is given by this expression actually. AR is equal to AR minus 1 plus AR minus 2, with A naught is 1, boundary condition, A naught is 1 and A1 is 1. So, A2 will be 2, A3 will be 3, A4 will be 5, and so on. But a closed form expression for this is given by this, AR is equal to 1 by root 5, 1 plus root 5 by 2 to the power of r plus 1 minus 1 by root 5, etc. Just check, put r is equal to 0, Fibonacci sequence. In that expression, put r is equal to 0, then A0 will be 1 by A, starting from 1, r is greater than or equal to 1, put r is equal to 1, then what is A1? A1 will be 1 by root 5 into 1 by 2 to 1 plus root 5 minus 1 by root 5, okay, into 1 minus root 5 by 2. So, first r is equal to 0 we have to consider. R is equal to 0, A0 will be 1 by root 5 into 1 plus root 5 by 2 minus 1 by root 5, 1 minus root 5 by 2, because you put r is equal to 0 there in that expression. This will be 1 by root 5 into root 5 by 2 plus root 5 by 2 is equal to 1. A naught is 1. So, that you can see. What about A1? R is equal to 1, this the whole square and this the whole square. A1 is given by 1 by root 5 this and this. Let us simplify and see this. A1 will be 1 by root 5 into 1 plus root 5 by 2 the whole squared minus 1 by root 5, 1 minus root 5 by 2 the whole squared, which will be 1 by root 5 you can take out, you can also take 4 out, then it will be 1 plus 2 root 5 plus root 5 minus 1 minus 2 plus 2 root 5 minus root 5 root 5 the whole square, root 5 the whole square, expanding. So, this will cancel with this will cancel with this will give you 1 by 4 root 5, 4 root 5 it is equal to 1. So, you can check that A naught is 1, A1 is 1, and similarly you can check that A2 is given by 2, A3 is 3, and so on. The generating function for that is Az equal to 1 by 1 minus z minus z square. So, this can be specified, the Fibonacci sequence can be specified in 3 different ways. This is a sequence. AR can be given by this closed form expression, or you can specify it by the difference equation, I mean generating function like this. The sequence can also be described by this relation AR is equal to AR minus 1 plus AR minus 2 with the condition that boundary conditions are A naught is equal to 1 and A1 is equal to 1. And this together with the boundary condition will specify the equation in a unique manner. This is called the recurrence relation for the Fibonacci sequence. Now, when you have a recurrence relation like that, how do you solve it? See, given the boundary conditions A naught, A1, etc., you can calculate A2, then A3 and so on. That way you can calculate, or you can also find the closed form expression. Now, how do you find the closed form? In the form of a generating expression or a simple expression like this in the general case. That is the what we want to study in this lecture. Generally, recurrence relation need not be linear, but we will concentrate on linear recurrence relation with constant coefficients. So, the example of Tower of Hana and this Fibonacci sequence, they are examples of linear recurrence relations with constant coefficients. A recurrence relation of the form C naught AR plus C1 AR minus 1 plus C2 AR minus 2 etc. equal to FR is a function of R, where Ci's are all constants, is called a linear recurrence relation with constant coefficients. This form is called a linear recurrence relation with constant coefficients. The above recurrence relation is also known as the kth order recurrence relation, provided both C naught and Ck are non-zero. For example, 2AR plus 3AR minus 1 is 2 power R. C naught AR plus C1 AR minus 1 is equal to 2R. This is a first order linear recurrence relation with constant coefficients. If you have something like this, the Fibonacci sequence, AR is equal to AR minus 1 plus AR minus 2, this is the Fibonacci sequence, or you can write AR minus 1 minus AR minus 2 is equal to 0, C naught is 1, C1 is minus 1, C2 is minus 1. This is a linear recurrence relation of the second order linear recurrence relation with constant coefficients. If you look at the expression for Tower of Hana problem, it is AN is equal to 2AN minus 1 plus 1. You can write it as AN minus, or I will write it here, AN minus 2, AN minus 1 is equal to 1, C naught is 1, C1 is minus 2, FR is 1, and this is linear recurrence relation of the first order with constant coefficient. So, in general, if you take like this particular example, this is, if you take, this is a first order linear recurrence relation with constant coefficients. Now, when you have a kth order linear recurrence relation, you can also call these recurrence relations as difference equations. Sometimes they are also called difference equations. If you have a kth order linear recurrence relation with constant coefficients, of course, with constant coefficients. It is of the form C naught AK plus C1 AK minus 1 etc. plus CK naught is equal to 0. Not 0, FR. Now, if you have consecutive values, some say AI plus 1 etc., AI plus K minus 1, K consecutive values of the function, this will give you the boundary condition. From this you can find out all the other values. Suppose I have the values for AI plus 1 etc., AI plus K minus 1, I can find the value of AI by K. From this I can find the value of AI plus K plus 1 and so on. Also from this I can find the value of AI minus 1 by rewriting the equation in a proper manner and solving it. So, given k consecutive values of the function, we can, that will give you the unique solution for the kth order, I mean the next value, any value you can find out in a unique manner by rewriting this equation in a proper way and solving that. For example, take the Fibonacci sequence, it is AR is equal to AR, I will write it AR minus 1, AR minus 2 is equal to 0. If I know that A3 is equal to, what is the value of A3 here? Look at the Fibonacci sequence. What is the value of A3? A0, A1, A2, A3 is 3, A4 is 5. Two values I have. A3 is 3, A4 is 5. From this you can find A5. A5 will be, from this you can write it as A3 plus A4. So, that will be 8. We can also find the value of A2 from this. How do you find A2? A2 will be A4 minus A3, that will be 2. And A1 will be A3 minus A2, that will be, what is A3 is 3, 3 minus 2 is equal to 1. Similarly, A0 you will be able to find as 1. So, by rewriting the equation properly, you can get all the values. Look at this recurrence relation, AR plus AR minus 1 plus AR minus 2 is equal to 4. This is a linear recurrence relation of the second order. If you get two consecutive values, say some AI and AI plus 1, if you have the values, you can calculate all the other values in a unique manner. Suppose I am given only one value. Suppose you are given A0 is equal to 2. Then the sequence cannot be determined uniquely. For example, you can see that 2, 0, 2, 2, 0, 2, 2, 0, 2 is, this is one sequence. A0 is 2, A1 is 0, A2 is 2. This will satisfy this recurrence relation. Another one is 2, 2, 0, 2, 2, 0. This also will satisfy the recurrence relation. Add these 3, you will get 4, add these 3, you will get 4, add these 3, you will get 4, and so on. So, the solution will not be unique if you just are given one value. If it is a kth order recurrence relation, you must have consecutive k values to get the proper sequence. If you are given more than one value, suppose I am given A0 is equal to 2, A1 is equal to 2, then it uniquely represents the sequence. Now, if A2 is also given, it should be given in a proper manner satisfying the equation, A2 should be 0. Otherwise, some other value is given means it will not satisfy the recurrence relation. This is not the correct thing, this is wrong. If A2 value also has to be given, it has to be given in a proper manner, adding A1 and A2, I mean satisfying the recurrence relation. if you are given fewer than that value, it is not unique. If you are given more than the required number of values, it has to be properly given, otherwise it may become inconsistent. Now, if it is not a recurrence relation, linear recurrence relation, if it is a recurrence relation of the form AR squared plus AR minus 1 is equal to 5, in that case this is first order. So, one value, if it is linear, one value should give you a solution uniquely, but this is not linear. So, giving A naught a particular value will not give you the solution in a unique manner. Supposing A naught is equal to 1, then 1, 2, will this satisfy this equation? 1, 4 plus 1, 5 it satisfies this equations. The third one can be A3 squared is equal to AR minus 1 plus 1. So, it could be root 3. Will this satisfy the equation? This squared 3 plus 2 5, correct. So, this will satisfy this equation. You can also see that 1 2 minus 3 root 3. If you, this sequence also will satisfy this equation, because you are taking the square root here. So, this squared plus this is 5, this squared plus this is 5, that is again satisfied. So, this equation will also satisfy the given recurrence relation. So, if it is linear, one value should give you the sequence in a unique manner, but because it is not linear, one value does not give the sequence in a unique manner. But we are concerned only with the linear recurrence relation with constant coefficients. So, this sort of a thing does not bother us anymore. A linear recurrence relation with constant coefficients, this is of the sum, this we have already seen. Now, before going into the solution of such linear recurrence relation, which has got two parts, the homogeneous solution and the particular solution. Now, we shall see how to find the homogeneous solution, how to find the particular solution and so on. But before going into that, let us consider one more example for formulating the recurrence relation. If you have a problem, sometimes it is easier to formulate it as a recurrence relation and then solve it. For example, in the case of Tower of Hana problem, the solution, the answer is 2 power n minus 1, which is not very obvious. Whereas, if you write it as AR is equal to 2 AR minus 1 plus 1, that is obvious. Okay? That sort of a recurrence relation, it is easy to write. So, what we would like to do is, given a problem, try to formulate the recurrence relation, and once we formulate the recurrence relation, then we can solve it. Let us consider one more example. In the plane, you draw ovals so that any one oval cuts the other ovals in exactly two places. So, if you have two ovals, it will cut like this. If you have a third oval, it will cut like this and so on. In how many regions the plane will be divided by such intersecting ovals? Another condition, there are two conditions, is every oval cuts any other in two places. That is, it is not something like this. For example, it is not like this. This cuts in 4 places. It is not like this, it is like this. Then secondly, no 2 points of intersection coincide. That all points of intersection are distinct, 2 of them do not coincide with like that. In that case, what is the number of regions created. What is the number of regions into which the plane is divided? That is what we want. For example, A naught does not have any meaning. A1 is one oval. If you draw one oval, it divides the plane into two regions. So, A1 is 2. What is A2? If you have two ovals, it will divide the plane into 4 regions. A2 is 4. If you have 3 ovals, how many regions you will have? 1, 2, 3, 4, 5, 6, 7, 8. So, A3 is 8. What about A4? You can have something like this. If you number, this 4 is here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It is divided into 14 regions. A4 is 14. What is the number for AR? What is AR? Or can you get a recurrence relation for this? The recurrence relation for this will be like this. Suppose AR is the number of regions into which the plane is divided when you have R ovals. AR is the number of regions into which the plane is divided into when you have R ovals. As AR minus 1 will be the number of regions into which the plane will be divided when you have R minus oval. What is the relationship between them? You see that after drawing R minus 1 ovals, the rth oval you are drawing, and it will intersect the first R minus 1 ovals, each one of them in 2 places. So, how many intersections will be there? There will be 2 into R minus 1 intersection for the rth oval. You have drawn R minus 1 ovals, and that has divided the plane into AR minus 1 parts. Now, you are drawing the rth oval, it will cut each one of the R minus 1 previous ovals in 2 points. So, totally there will be 2 into R minus 1 points of intersection for the rth oval. That is because we have assumed that no 3 points of intersection, no 2 points of intersection coincide. I think not 3 points, any 2 points of intersection do not coincide. I mean the points of intersection are all distinct. In that case, the rth oval is divided into 2 into R minus 1 arcs. The rth oval when you draw, it is divided by the point of intersections at 2 into R minus 1 places. That is, this oval is divided into 2 into R minus 1 arcs. Now, you see that if you take this arc divides the earlier region. This region is divided into 2 parts by this arc. So, each one of this 2 into R minus 1 arcs, each one of them will divide one region into 2 regions. So, that will be 2 into R minus 1 new regions will be created. So, the recurrence relation will be the number of regions into which R ovals will divide the plane is what you already have by drawing R minus 1 ovals, plus the rth oval has been cut into 2 into R minus 1 places, and it is divided into 2 into R minus 1 arcs. Each one of the arc divides one of the original region into 2 regions. With that, 2 into R minus 1 new regions are created. So, AR is given by this expression. AR is equal to AR minus 1 plus 2 into R minus 1. With this, we can see that what will be the value for A5? What will be the value for A5? A5 will be A4 plus 2 into 5 minus 1, that is 14 plus 2 into 4 equal to 22. And similarly, you can calculate that A6 is 32 and so on. So, this is the recurrence relation. It is a linear recurrence relation with constant coefficients. Let us consider another problem. It is like this. For n is equal to 0, 1, 2, etc., let H2n denote the number of regions into which a plane is divided by n lines in general position. That is, every pair of lines meet in exactly one point, but no 3 lines meet in a point. For n is equal to 0, 1, 2, etc., let H3n denote the number of regions into which the space is divided by n planes in general position. By general position, we mean every pair of planes but no 3 planes meet in a line, every 3 planes but no 4 planes meet in one point. Determine formulas for H2n and H3n. This is the problem. So, let us see how we can form a recurrence relation and find a solution for this. So, H2n means in a plane you are drawing n lines and find out the number of regions into which the plane is divided. You can see that H21 will be, if you draw one line, then the plane will be divided into 2 regions. So, H21 will be 2, H22 will be, if you draw 2 lines, the plane will be divided into 4 regions. Now, instead of considering H2, if we consider H1, the one dimensional case, a line is divided by points. So, if you have one point H11, this line will be divided into 2 parts. If you have 2 points, the line will be divided into 3 parts. H10, there is only one, that is 1, and if you have n points, the line will be divided into n plus 1 line segments. The relation here is H1 n equal to H1 n minus 1 plus 1. We can make use of this H1n for writing the recurrence for H2. Suppose you are having n minus 1 lines, then the plane is divided into H2 n minus 1 regions. Now, we want to express H2n in terms of H2 n minus 1 something else. What is that? Now, the plane is divided into some regions. If you want to add one more line, then this one more line is cut by n minus 1 lines. So, how many line segments the new one will have? The new one will have H1 n minus 1 line segments, and each one of these line segments will divide an already existing region into 2 regions. So, it will add one more region to this. So, the recurrence relation is given by this. H2n is equal to H2n minus 1 plus H1 n minus 1. Now, making use of this, if you try to solve, I will just write down like this: H2n minus H2 n minus 1 is equal to H1 n minus 1, H2 n minus 1 minus H2 n minus 2 is equal to H1 n minus 2 and so on. Finally, H2 1 minus H2 0 equal to H1 0. Now, if you add them, this will get cancelled and so on. finally you will get H2n minus H20 equal to H10 plus H11 up to H1n minus 1. Now what is this? H10 is 1, H11 is 2, H1n minus 1 is n. So this reduces to n into n plus 1 by 2. So what can you say about H2n? H2n, H20 is when no lines are drawn, the plane has only one region. So H20 is equal to 1. So H2n minus 1 is equal to n into n plus 1 by 2. And this gives you the answer. H2n is equal to 1 plus n into n plus 1 by 2. Now check the answer with 1, n is equal to 1, you put 1, 1 plus H2 1 will be 1 plus 1 into 1 plus 1 by 2, which will be 1 plus 1 equal to 2, which is we have already seen that is correct. What about H22? H22 will be 1 plus 2 into 2 plus 1 by 2, that is 1 plus 3 equal to 4. This is also we have seen. Now a fact to note is you can write H1n as n0 plus n1. What is nc0, nc1? What is this? This will be just 1 and this will be n. You know that H1n is n plus 1. If you look at H2n, this you can also write as n0 plus n1 plus n2, because what is this? This is 1, this is n, plus nc2 is n into n minus 1 by 2. If you simplify this, 1 plus 2n plus n squared minus n by 2, that will be 1 plus n into n plus 1 by 2. Now coming to the 3-dimensional case, a similar argument will tell you that H3n equal to H3n minus 1 plus, that is when you have n minus 1 planes, the space is divided into so many regions, that is given by H3n minus 1. When you add the nth plane, that nth plane will be divided into, in that particular plane it will be divided into H2 into H2n minus 1 regions, and each one of those plane segment will divide a 3-dimensional region into 2, that is adding one more. So the recurrence relation for that will be like this. Again, if you use the same argument and try to solve, you will see that H3n is equal to n0 plus n1 plus n2 plus n3. The working out, I will leave it as an exercise to you. How do you go about solving such a linear recurrence equation? This is what we want to see next. Given the recurrence relation or the difference equation, how do we get the expression for AR? This is known as the solution, finding the solution to the linear difference equation. The solution to the linear difference equation with constant coefficients is the sum of two parts: the homogeneous solution, which satisfies the difference equation when the right hand side of the equation is set to 0, and a particular solution which satisfies the difference with FR on the right hand side. So the solution consists of two parts: the homogeneous solutions and the particular solution. The homogeneous solution is obtained when you set the right hand side to 0, and the particular solution is when you set the right hand side to FR. In other words, discrete numeric function, that is the solution of the difference equation, is the sum of two discrete numeric functions. One is the homogeneous solution and the other is the particular solution. The homogeneous solution is given like this. Let H, H denotes homogeneous. It is a sequence like this. A naught, it is a discrete function, a sequence A naught H, A1H, ARH and so on, denote the homogeneous solution, and the particular solution is given by AP. P denotes the particular solution, A naught P, A1P and so on. This denotes the particular solution to the difference equation. The total solution is the sum of these two. So, how do you get the homogeneous solution? The difference equation is of this form with the right hand side FR, but when you want to find the homogeneous solution, you set it as C naught ARH plus C1 AR minus 1 etc. to 0. The right hand side is set to 0, and the particular solution is obtained by putting the equation and the FR, whatever value was originally there here. So, when you add up these two, you will get C naught ARH plus ARP etc. This is the total solution, and this is, when you add the right hand side, it is 0 plus FR is FR. The total solution is A is equal to AH plus AP, satisfies the difference equation. This we can see. But the question is, why do you have to find the homogeneous solution? Why do you have to find the particular solution? Because homogeneous solution, the right hand side, you are making it different. Why do we do this? The reason is we have some boundary conditions, and the boundary conditions have to satisfy the equation, and in general it is advised only if you take the particular solution alone, it may not satisfy the boundary condition, but if you take a total solution, it will definitely satisfy the boundary condition and so on. So, next step is, how do you go about finding the homogeneous solution? How do we go about finding the particular solution? The homogeneous solutions are obtained in this manner. A homogeneous solution of a linear difference equation with constant coefficients is of the form A alpha 1 R, where alpha 1 is called a characteristic root and A is a constant determined by the boundary conditions. So, this homogeneous solution, it is of the form A alpha 1 power R, where alpha 1 is a characteristic root. Let us see how this happens. Suppose you have A alpha R in the AR, the difference equation with right hand side equal to C0, then you have C naught A alpha R plus C1 A alpha R minus 1 plus C2 A alpha R minus 2 etc. Ck A alpha R minus k equal to 0. You get this if you substitute A alpha R for AR. Then this equation becomes C naught A power k plus C1 A k minus 1 plus C2 A k minus 1 and etc. plus Ck is equal to 0, which is a polynomial of degree k in A. And if you find the roots of this equation, that will be the characteristic, that will give you the characteristic roots. So, this equation is called the characteristic equation of the difference equation. Therefore, if alpha is one of the roots of the characteristic equation, then A alpha 1 R is a homogeneous solution for the difference equation, because the root of this equation will satisfy the recurrence relation with the right hand side set to 0. So, let us see how this happens. For example, in the Fibonacci sequence, we had AR is equal to AR minus 1 plus AR minus 2, or AR minus AR minus 1 minus AR minus 2 equal to 0. So, the characteristic equation is alpha squared minus alpha minus 1 is equal to 0. What are the roots of this equation? Minus 1 plus or minus square root of b squared minus 4ac, that is 4 by 2. So, the roots are 1 plus root 5 by 2, 1 minus root 5 by 2. These are the two roots. If you have alpha 1 as a root, that will satisfy this equation. So, what we have is the solution for this is AR is of the form some A1 1 plus root 5 by 2 to the power of R plus A2 into 1 minus root 5 by 2 to the power of R, and A1 and A2 have to be determined from the boundary conditions. A characteristic equation of kth degree has k characteristic roots. Suppose the roots of the characteristic equations are all distinct. In this case, it is easy to verify that the homogeneous solution ARH is A1 alpha 1 R plus A2 alpha 2 R etc. AK alpha k R. This is a homogeneous solution to the difference equation, where alpha 1 alpha 2 alpha k are the distinct characteristic roots and A1 A2 AK are constants which are to be determined by the boundary conditions. So, in this case we can see that 1 plus root 5 by 2, 1 minus root 5 by 2 are distinct roots of this equation. This is a second order linear difference equation with constant coefficients. And if you write the characteristic equation, it is this equation. The roots of this equation are given by this. So, the homogeneous solution will be of this form, where the constants A1 and A2 have to be determined using the boundary condition. Now, what is A naught? A naught is 1 and A1 is 1. This we know, starting points are A naught is 1 and A1 is 1. So, putting R is equal to 0, you will get 1 is equal to A1 plus A2, and put R is equal to 1, you will get A1 into 1 plus root 5 by 2 plus A2 into 1 minus root 5 by 2, that is equal to 1. But what is A1? A1 is 1 minus A2. So, 1 minus A2 into 1 plus root 5 by 2 plus A2 into 1 minus root 5 by 2 equal to 1, which will give you A2 into 1 minus root 5 by 2 minus 1 plus root 5 by 2, that is the left hand side, equal to 1 minus 1 plus root 5 by 2. So, this will give you A2 into 1 minus root 5 minus 1 plus root 5 by 2 minus root 5 by 2 equal to 2 minus 1 minus root 5 by 2. That is, A2 will be 1 minus root 5 by 2 root 5 minus with a minus sign. So, A2 will be 1 by root 5 minus 1 by root 5, 1 minus root 5 by 2. And similarly, if you calculate, A1 will be 1 by root 5, 1 plus root 5 by 2. So, using this value of A1 like this, and A2 is, we have seen, minus 1 by root 5, 1 minus root 5 by 2 Using this, in this equation, the solution, homogeneous solution becomes AR is equal to 1 by root 5, 1 plus root 5 by 2 R plus 1 minus 1 by root 5, 1 minus root 5 by 2 to the power of R plus 1. Here we had 1 plus root 5 by 2 to the power of R, but A1 we have found to be this value. So, putting that you get this term, and here we have A2 into 1 minus root 5 by 2 to the power of R, and A2 is this value. So, putting that here you get the solution, homogeneous solution for AR like this. So, this is when the characteristic roots are all different. Now, if you have multiple roots, what is a homogeneous solution? And when you find the homogeneous solution, how will you find the particular solution? These are some of the things we have to consider next. So, these will be considered in the next lecture.